So in this video, we're going to talk about how we can determine the total potential energy of a single bar element, and we're going to use the RRitz method to define the strain. We use it to define the relationship between force and displacement within our element. So if you recall from the RRitz method that the total potential energy pi of the system was equal to the strain energy U minus the external work being done on the element. So to solve for, so we said that we could assume some type of function v of x, where v of x was the displacement function. We were able to then solve a system of equations in order to determine any unknown constant. So typically we assume some type of polynomial in our system. So we assume something like a1 plus a0 plus a1x or something like that. Right, and if we took the derivative with respect of pi with respect to those unknown constants, we could then solve for those unknown constants. Right. So in the finite element case, what we're going to do is, instead of taking the derivative with respect to a naught and ai, we're going to take the derivative with respect to the displacements at the nodes, and we're going to treat those as our unknown constants. So that's what u of I is. Okay. So if we take the derivative of our total potential energy with respect to I, we have to recall that the total potential energy of our element is equal to the u of the element minus w of the element. So in the last couple of videos, we talked about how we could define the potential energy of the element as being equal to the displacement of the element transposed times the stiffness matrix of the element times the displacement matrix of the element, and then we can then subtract the external work being done on our element, which would be u of I times fx of I and u of I times fx of j. All right. So I think that's a typo. I believe that should be u of j, not u of I. Sorry. Here. All right. So if we take the derivative with respect to u of I and u of j, and we set that both of those equal to 0, and we set we basically will end up with two equations which we can write in matrix form here, and then if we move the fxi and fxj terms to the other side, we'll end up getting this equation here. All right. So we can then use this equation to solve for our unknown. So this equation actually should look relatively familiar. I know it's written in matrix form, so it might be a little bit hard to see, but it's actually this is actually just Hooke's law. So Hooke's law says is that if we have a spring and we have a force being applied on one end of our spring, and we can say at the other end is fixed. In this case, our fx, we can say we'll call this node I, and we'll call this node j here. And then this would be our displacement u of I, and this would be our displacement u of j. Okay, we know that the force at fx of j would be equal to F. The force being applied at point I would be equal to is unknown at this point, and then the displacement at point I is 0, and the displacement at point j is unknown. Okay, so we can solve for those unknowns if we use we can solve for our unknown u of j using this equation up here. So if we do that, we can say that fx, so what we're going to do is we're going to use the bottom row of this matrix here to solve for fxj. So if we say fxj would be equal to a e over L times u of j minus u of I, all right? U of I we know is 0, all right? So we could say that Fx, or a force applied to our spring, would be equal to K, which is equal to AE over L for a elastic material, times U of J, which would be our delta X. Okay? So this is our this is how you can relate Hooke's law for a simple spring back to our to the finite element definition for a bar element.